James Webb just found a black hole that shouldn't exist. It's growing so impossibly fast that physicists are scrambling to rewrite the laws of the universe. And the worst part? We have no idea how it got that way. This discovery represents one of the most significant challenges to our fundamental understanding of cosmology and astrophysical processes in recent memory. For more than a century, our understanding of black holes has been built on Einstein's theories and decades of observation. We know how they form, how they feed, and how they grow, or at least we thought we did. The foundation of black hole physics was laid by Einstein's revolutionary general relativity, which predicted that massive objects curve space-time itself. Carl Schwarzschild was the first to find an exact mathematical solution to Einstein's equations describing a black hole. But in November 2024, the James Webb Space Telescope captured something that completely obliterates everything we believed about the early universe and the cosmic objects that inhabit it. A single discovery has shaken the very foundations of cosmology and left researchers across the globe scrambling to find answers to questions they never thought they would need to ask. This is the story of that discovery and what it means for our understanding of the cosmos itself and our place within it. The discovery will likely reshape graduate curricula and textbooks for years to come. Let me take you back to the very beginning of time itself, or as close as we can possibly get with our current technology and scientific capabilities. Just 570 million years after the Big Bang, when the universe was still in its infancy and barely more than a cosmic child, there existed a galaxy we now call Canucks LRD Z86. This isn't just any ordinary galaxy that you might find in the modern universe. It belongs to a mysterious and enigmatic class of objects that astronomers have affectionately nicknamed the little red dots, or LRDs. These are small, extremely distant, and strikingly red objects that the James Webb Space Telescope has been discovering with increasing frequency since it began its revolutionary observations in 2022. They represent some of the oldest structures we've ever observed. Precious windows into a universe so young that most stars had barely begun to shine and undergo their nuclear fusion processes. These objects have mystified the astronomical community from the moment they were first detected, challenging our existing models and theories. The discovery of little red dots was unexpected, as conventional models predicted that such luminous objects shouldn't exist at such early cosmic epochs. Their presence suggested either rapid star formation, supermassive black holes, or both simultaneously occurring in these compact systems. But what makes Canucks LRD Z8.6 truly extraordinary isn't its incredible age or its striking red color in the infrared spectrum, which itself is remarkable. It's what's happening inside it. It's what lies at the very heart of this galaxy, at the very center of this cosmic structure. At the center of this distant galaxy lies a supermassive black hole, and this isn't just any run-of-the-mill supermassive black hole that quietly lurks in galactic centers. This black hole is actively feeding, actively consuming the material around it with unprecedented intensity, and it's doing so at a rate that fundamentally defies the laws of physics as we currently understand them. When the James Webb Space Telescope's remarkable near-infrared spectrograph, or NIRSpec, pointed its sophisticated instruments at this incredibly distant galaxy and carefully analyzed the light streaming from its energetic core, the data told a story that seemed almost impossible to comprehend. The observations were confirmed and verified by multiple independent spectroscopic measurements taken over several observation sessions. The consistency of the measurements across different instrumental configurations and observation dates provided confidence in the robustness of the findings. Astronomers rarely encounter data this unambiguous and definitive about such extreme physical processes occurring in the universe. The team of researchers who made this groundbreaking discovery, led by Roberta Tripodi from the prestigious University of Ljubljana in Slovenia and the Osservatorio Astronomico di Roma in Italy were the first to witness what appears to be one of the most extreme and violent black holes in the entire observable universe. What they found was genuinely staggering and shocking to the scientific community. The black hole at the very center of Cannax LRD Z86 is actively accreting matter, which means it's pulling material from its surroundings and consuming it at a rate that is orders of magnitude greater than what should theoretically be possible according to our established models and physical laws. To put it simply and directly, this black hole is eating too fast. It's eating far too fast. The rate of consumption exceeds all theoretical predictions by a factor of 40. Now, you might be wondering what exactly makes a black hole eat too fast, or what that even means in practical terms. This brings us to a fundamental concept in astrophysics called the Eddington limit, a principle that has been absolutely fundamental to our understanding of black hole physics and accretion phenomena for nearly a century. Named after the brilliant British astrophysicist Arthur Eddington, who developed this concept in the early 20th century, this limit describes precisely the maximum rate at which a black hole can accrete matter while still maintaining a stable and coherent structure. The Eddington limit represents a critical equilibrium point between competing physical forces that govern the behavior of infalling matter. It exists because of a delicate balance between two opposing forces that are constantly at war with each other. On one hand, gravity pulls material toward the black hole, accelerating it to incredible speeds and temperatures as it spirals inward, following geodesic paths through warped space-time. On the other hand, the intense radiation produced by the friction and tremendous heat of all this infalling material pushes back. The limit was originally calculated to maintain equilibrium between gravitational attraction and radiative repulsion. In mathematical terms, the Eddington limit defines the point where the outward radiation pressure precisely balances the inward gravitational force on matter in the accretion disk surrounding the black hole. But the black hole in Cannax LRD Z86 appears to be dramatically violating this supposedly fundamental limit. According to the detailed analysis of Webb's spectroscopic data, this black hole is accreting matter at approximately 40 times the theoretical Eddington limit. Let that sink in for a moment. Not just slightly above the limit, not just significantly above it. The implications of this extraordinary discovery are absolutely staggering and far-reaching, extending to every corner of modern cosmology. For decades, we've known with certainty that supermassive black holes exist at the centers of most large galaxies, including our own Milky Way, where Sagittarius A resides quietly and has a mass of approximately 4.1 million solar masses. We've also known that in the early universe, there are supermassive black holes that are far larger than they should be, according to our models and theoretical predictions. Some of these ultramassive black holes discovered by various surveys contain billions of solar masses. How a black hole can grow to such enormous sizes in such a relatively short cosmic time frame has been one of the great unsolved mysteries of astronomy. There simply isn't enough time, according to our current models and calculations, for these objects to have grown to their observed sizes if they're only feeding at the normal Eddington limit. Detailed calculations by theorists suggest that normal Eddington-limited accretion would take tens of billions of years to grow black holes to their observed sizes, far longer than the age of the early universe. This problem is known as the black hole formation problem, or the early black hole problem, and it's been puzzling and frustrating astronomers for many years. Every time astronomers look deeper into space and farther back in time, they find black holes that shouldn't exist yet, shouldn't be that massive, and shouldn't have had enough time to grow to their observed sizes. This has been one of the most perplexing issues in modern astrophysics, spawning numerous theoretical papers and observational campaigns. The discovery of Cannax LRD Z8.6 suggests that the answer might be super Eddington accretion, a fascinating process in which black holes pull in matter at rates that dramatically exceed the theoretical limit. But even this tantalizing explanation has significant challenges and complications that researchers must carefully consider. How can this extreme feeding happen consistently and reliably across multiple objects? How can a black hole maintain such an intense feeding rate for an extended period without tearing itself apart or violating fundamental physics? And perhaps even more importantly, why is this particular black hole doing this, while most other black holes in the universe seem to follow the established rules and stick to the Eddington limit? These questions continue to perplex researchers worldwide. The research team used Webb's truly exceptional and revolutionary capabilities to reveal exactly what's happening deep inside this distant and ancient galaxy. They carefully analyzed the spectrum of light coming directly from the black hole's accretion disk, the swirling, superheated disk of material spiraling into the black hole at nearly the speed of light. The spectrum revealed something absolutely remarkable and telling: gas that had been highly ionized and energized by intense energetic radiation, and clear evidence that this gas was rotating quickly around a central source. These are the unmistakable telltale signatures of an actively accreting, supermassive black hole consuming material at tremendous rates. The spectral features observed provided unambiguous evidence of violent accretion processes. The spectral data also allowed the team to precisely measure the black hole's mass, and what they discovered was almost as shocking and astonishing as the accretion rate itself. The measurements revealed a black hole far more massive than expected for such an early epoch. The black hole in Canucks LRD Z8.6 is unusually and remarkably massive for such an early stage in the universe's history. Even more remarkably, it appears to be overmassive relative to its host galaxy. In the modern universe that we observe today, astronomers have documented a consistent and reliable relationship between the mass of a supermassive black hole and the mass of stars in its host galaxy. Typically, a black hole's mass is about 0.1% of the stellar mass of its galaxy, a relationship that holds across billions of galaxies. This relationship is so consistent and reliable that it's known as the black hole mass-galaxy relation, and it appears to be nearly universal across the cosmos. But Canucks LRD Z8.6 brazenly breaks this fundamental rule. Its central black hole is far more massive than this well-established relation would predict. For such an early galaxy, when everything should theoretically be smaller and less massive, finding a black hole that's already this enormous is like finding a fully grown adult in a nursery full of infants. This represents a fundamental departure from what astronomers expect. This landmark discovery connects directly to one of the most profound and intriguing mysteries in astronomy: the little red dots themselves. These mysterious and enigmatic objects have been appearing in Webb's observations with increasing frequency and regularity, confounding researchers and challenging established theories. The astronomical community still doesn't fully understand what they are or why they're so remarkably luminous for their size. Some researchers have speculated that they might be black hole-dominated galaxies, systems where the black hole dominates the energy output rather than the stars. The groundbreaking discovery in Canucks LRD Z8.6 strongly supports this compelling hypothesis and suggests that these little red dots might be uniquely extreme environments where black holes are undergoing periods of rapid and intense growth. The evidence provided by this discovery is compelling and substantial. But there's another significant layer to this fascinating story that adds even more mystery and complexity to our understanding. In November 2024, just weeks after the Canucks LRD Z8.6 discovery was officially announced and published in peer-reviewed journals, another team of astronomers reported finding an even more extreme black hole. This one, designated LID 538, appeared to be accreting matter at an astounding 40 times the Eddington limit, making it seem like a record-breaking discovery that would surpass the initial findings. The discoveries seem to strongly suggest that the early universe was filled with these impossibly fast-feeding black holes, pulling in material at extreme rates. But then came a plot twist that nobody in the astronomical community expected. Subsequent careful reanalysis and examination of the observations suggested that the extreme accretion rate initially calculated for LID 568 might have been a significant overestimate due to observational uncertainties. Heavy dust and cosmic debris obscuring the black hole had apparently led to incorrect calculations in the initial analysis. When the data was thoroughly reanalyzed with more sophisticated models and better dust extinction corrections, the black hole turned out to be far less extreme than initially believed. However, even with this important correction and revision, the black hole in Kananuk's LRD Z8.6 remained definitively and unquestionably extreme, a genuine and confirmed violation of our theoretical predictions that withstand scrutiny. This brings us to the very heart of the mystery and the central question that drives current research throughout the astronomical community. If a black hole can accrete matter at rates that exceed the established Eddington limit, how does it actually accomplish this? How can the laws of physics allow this to happen? One fascinating possibility that theoretical physicists have carefully considered is something called super-Eddington accretion. In this intriguing scenario, the radiation produced by the infalling material isn't directed uniformly outward in all directions as traditional models assume. Instead, much of the radiation escapes in particular directions, creating anisotropic radiation fields that allow additional material to continue falling inward without being completely blocked by radiation pressure. This can happen when the accretion disk is oriented in particular geometries, or when the disk itself is thick enough to shield certain regions from radiation, creating anisotropic outflows and reducing effective radiation pressure. The geometry of magnetic field lines plays a crucial role in determining the distribution and escape of radiation. Another important mechanism that physicists have identified involves powerful magnetic fields threading through the system. Powerful magnetic fields threading through the accretion disk can redirect radiation and potentially increase the accretion rate significantly beyond the theoretical limit that was previously thought to be absolute and immutable. These magnetic fields can channel jets of material away from the accretion disk, reducing radiation pressure in the equatorial plane and enabling enhanced accretion rates. The early universe appears to have been an environment uniquely and ideally suited to these extreme conditions and violent processes. In the first few 100 million years after the Big Bang, galaxies were dramatically smaller, more compact, and far denser than they are in the modern universe. The intergalactic medium was filled with abundant hydrogen and helium, providing tremendous fuel for both rapid star formation and accelerated black hole growth. In these dense and gas-rich environments, black holes might have experienced brief but intensely violent growth spurts, pulling in matter far faster than they can today under typical circumstances. The universe has continuously expanded and cooled significantly since then, and the density of available fuel has decreased dramatically as space has expanded following the predictions of general relativity and cosmological models. Black holes today must make do with far less food and material, which is why they must strictly follow the Eddington limit in our current epoch. The conditions that enabled such rapid accretion have essentially vanished as the universe evolved from its primordial state. Today's black holes operate in an environment fundamentally different from that of their ancient predecessors. The team analyzing Canucks LRD Z8.6 was led by Roberta Tripodi, who emphasized that the discovery was truly and genuinely remarkable in every conceivable way. They had successfully observed a galaxy from less than 600 million years after the Big Bang, hosting not just any supermassive black hole, but one growing far faster than anyone expected at such an early time in cosmic history. This fundamentally challenges our understanding of black hole and galaxy formation in the early universe and opens entirely new avenues of research for the scientific community. The implications continue to reverberate through the astronomical community and inspire new theoretical models. The data from Webb was absolutely crucial and irreplaceable to making this discovery possible. Previous technology and instrumentation simply couldn't have revealed these critical details about distant galaxies and their black holes. The spectral features that pointed to the accreting black hole, the precise measurements of the black hole's mass, and the detailed comparison of the black hole mass to the stellar mass would have been entirely impossible without Webb's revolutionary and unprecedented infrared capabilities and spectroscopic prowess. Webb's sensitivity extends to wavelengths where dust obscuration is minimal, allowing observations that ground-based and previous space-based telescopes simply could not achieve. The mission has fundamentally transformed observational astronomy in ways that continue to surprise researchers with each new discovery. What makes this discovery even more compelling is what the spectroscopic data reveals about the relationship between the black hole and its galaxy. In Canucks LRD Z8.6, the black hole appears to have grown faster than the galaxy itself has grown throughout its history. This profound observation suggests that black holes in the early universe may have formed first, or at least grown much more rapidly than the galaxies surrounding them. This significantly inverts our current understanding of black hole and galaxy coevolution and their mutual development. We've long believed that galaxies and their central black holes grow together over time, influencing each other through complex feedback mechanisms and regulatory processes that connect them dynamically. But if black holes can outpace their galaxies in growth rates, then the relationship is far more complex and nuanced than we previously imagined. It suggests that black holes might form in unexpected ways in the early universe, possibly from the direct collapse of massive clouds of gas without first requiring stellar processes, or through exotic mechanisms we haven't yet discovered or properly understood. The research team is already planning to conduct additional observations using the Atacama Large Millimeter Array, or ALMA, one of the most powerful radio telescopes ever constructed. This array consists of 66 radio dishes working in concert to provide unprecedented sensitivity to millimeter and submillimeter wavelengths. They will also pursue more comprehensive follow-up observations with Webb itself to gather additional data and seek additional signatures of extreme accretion. These future observations will focus intensely on the cold gas and dust in the galaxy, allowing researchers to better understand exactly how much fuel is available for the black hole to continue consuming and sustaining its extreme feeding rate. They hope to find more galaxies like Canucks LRD Z8.6, little red dots, with similarly extreme black holes at their centers. Each new discovery will provide crucial clues about how the early universe operated and how the rules of physics manifested in those ancient times before the universe had completed its first billion years. These observations represent the next frontier in understanding cosmic evolution and the fundamental processes that shaped galaxies and their central black holes during the early universe. The implications extend far beyond this single remarkable galaxy and its contents. If early universe black holes could grow at super Eddington rates, then this resolves at least part of the black hole formation problem that has plagued astronomy for many years. It explains how black holes could have reached billion solar mass sizes by the time the universe was only a billion years old, a timeline that previously seemed impossibly compressed. It explains why we consistently keep finding these impossibly massive black holes when we look deep into space and far back in time. The universe's early black holes weren't necessarily growing in exotic ways or through mysterious mechanisms we don't understand and cannot explain. They were simply growing fast, taking full advantage of the dense, gas-rich environments that existed in the infant cosmos. This represents a more parsimonious explanation grounded in known physics. But this also raises entirely new questions for the scientific community and researchers worldwide. If black holes grew rapidly in the early universe, what happened to that growth? Why do black holes today appear to grow much more slowly than their ancient ancestors? The answer likely lies in the continuous evolution of the universe itself and its changing physical conditions. As the universe expanded over billions of years, the density of available fuel and material decreased significantly. Galaxies became more spread out and isolated from one another, the intergalactic medium became more rarefied and sparse, and the conditions that allowed for super-Eddington accretion became increasingly rare and unusual. By the time the universe reached 1 billion years of age, the era of rapid black hole growth had largely ended. Black holes today must compete for the remaining fuel and material, and they do so under strict adherence to the Eddington limit that governs their behavior. The physical landscape has transformed entirely. The discovery of Canucks LRD Z8.6 also has profound implications for our understanding of the little red dots as a distinct class of objects worthy of special attention. These mysterious galaxies have continuously puzzled and challenged astronomers since they began appearing regularly in Webb's observations. They're far too luminous for their apparent size, producing far more light than a galaxy of their stellar mass should theoretically produce, according to standard stellar physics. One explanation that has been proposed has always been that they're powered by actively feeding supermassive black holes, and the discovery of the extreme black hole in Canucks LRD Z8.6 strongly validates this compelling hypothesis. If many little red dots indeed host similar black holes feeding at extreme rates, then that perfectly explains their anomalously high brightness. These aren't normal galaxies dominated by stars and stellar processes. They're black hole systems, unique environments, where the black hole is the primary and dominant engine of light and energy output. The model fits the observational data remarkably well. Looking forward to the future with optimism and scientific curiosity, this remarkable discovery represents just the beginning of a completely new era in our understanding of the early universe. The James Webb Space Telescope, with its unprecedented infrared sensitivity and powerful spectroscopic capabilities, is revealing a cosmos that is very different from the one we thought existed. For many decades, our view of the early universe was severely limited by the capabilities of previous telescopes. Hubble could see far back in time, but it operated primarily in visible light, which gets shifted far into the infrared by cosmic expansion and redshift effects. The most distant objects appeared as mere faint specks, their properties impossible to determine with certainty. As the James Webb Space Telescope continues its observations over the coming years and decades, we expect to find more galaxies like Canucks LRD Z8.6 with extreme characteristics and unusual properties. We expect to find more little red dots powered by extreme black holes consuming matter at unprecedented rates never before documented. We expect to find surprises that once again challenge our established theories and force us to reconsider our assumptions about fundamental physics. This is ultimately how science progresses and advances through iterative cycles of observation and revision. We make observations, we build theories to explain them, and then we make more observations that force us to revise and improve our theories. The James Webb Space Telescope is taking us deeper into that productive cycle than ever before, revealing an early universe that is far more complex and extreme than anyone previously predicted or imagined. The black hole in Canucks LRD Z86 is is just one piece of an enormous cosmic puzzle that astronomers are now racing to solve through intensive observation programs. What we learn from this galaxy and others like it will fundamentally shape our understanding of the cosmos for generations to come and reshape the foundations of modern cosmology.